Okay, now we have enough information that we can start talking about radiation patterns and antenna radiation in a little bit more engineering detail. So from our discussion on plane waves several videos ago, you'll remember that you can calculate the power transmitted by an EM wave using the pointing vector. It tells you power and direction that a plane wave, the power and the direction of power transfer for a plane wave. And the pointing vector is given by the cross product of the electric field and the magnetic field. I almost wrote M for magnetic field. We all know that's an H, and that's measured in watts per meter squared. Most commonly, we're not interested in instantaneous pointing vector. However, we're looking at the time average power density, or the time average pointing vector. We indicate that as capital P average, and that's equal to 1/2 the real portion of E cross H complex conjugate. That is still measured in watts per meter squared. So that's just the power contained in the plane wave. And for an antenna, the result of the pointing vector is often called radiation density or radiation power density. So they give it a different name for antennas, radiation power density. It's just the pointing vector, though. So since the pointing vector, it's giving us a power density, we can calculate the total power radiated by an antenna well, maybe let me step back for a second. Remember that this is P av of R theta phi, right? It's telling us the power in a particular point in space due to an electromagnetic wave. Well, what if we want to consider all points in space, which is just the total sphere? And if we want to calculate total power radiated by an antenna, we have to know, well, what is the pointing vector for all points in space? So how do I sum up the pointing vector for all points in space? Well, I have to integrate that. Well, the problem is that I got to integrate over 2 dimensions, right? I got to integrate over all space. And so how I would write that is the radiated power, the total power radiated by an antenna, is going to be given by the surface integral of the time averaged pointing vector. And since it's a surface integral, I need to integrate with respect to this little surface element, which is why we had that tangent in that last video of ds. And if I take that integral, the surface integral of P average of R theta phi ds, then that's going to give me my total power in watts. And we already determined that the surface integral here, ds, we developed the formula for that, and so we can just write that as the surface integral of P average, and we can get rid of this ds element, and we can write it in terms of spherical coordinates as r squared sine theta d theta d phi. And this is the formula that we will most always use to determine total power radiated by an antenna, is this surface integral. And its equation for total power radiated by an antenna, and its units are going to be in watts, right? Total power is going to be watts. So what does radiation power density really tell you? Well, at the end of this power density up here, it's going to be a function of a position in space. So it's telling us the power received at a certain point in space. So if I've got an antenna and I'm surround that with 3 dimensions, well, what if I want to know the power over here, or the power over here, or the power at maybe a smaller sphere? What's the power on the surface of that, right? That's what radiation power density is telling you, is what is the density of power at a specific point in space. Power received at a certain point in space, measured away from the source of radiation. So the way I like to think of it is, how much power is available from the sun's light at Earth. Obviously, this is going to be dependent on the strength of the EM radiation emitted by the sun, but also the direction that the sun's EM radiation is going to be emitted in, and also how far away you are from the sun in a certain direction. And that's radiation power density. And so it's important to note that radiation power density here is a function of all 3 space variables, r, theta, and phi. And as I stated in an earlier video, radiation patterns, the drawings that we make of the shape of radiation, whether it's spherical or directional or something like that, those are usually normalized. And so if we normalize power here, we get P of r theta phi. We normalize that. How do we normalize it? Well, when we're creating our power plots, we normalize it by dividing it by the maximum power. So that would be, this power point right here. We divide it by maximum power at some specific r theta phi, right? That's occurring at a specific point in space. And so what's going to happen is that this r dependency drops out, and we get what's called a normalized power pattern. That's linear. If we take 10 log of that, it's in dB, so it can either be unitless or in dB. And this really is what we're plotting on the radiation plots, this normalized power pattern right here. So let's do an example to maybe understand that a little bit. And we want to compare the total power radiated by an antenna. And this antenna has a radiation density function of A0 sine theta over r squared, pointing in the radial direction, watts per meter squared. So that's just my, that's the result of my pointing vector. It's given to me. And I want to compare that to the total radiation by an isotropic emitter with the same peak power density. So here A0 is the peak power density, and we can see that the pointing vector is only a function of theta and r here. And so to determine total radiated power from the formula that was given before, I need to perform the surface integral of the power vector multiplied by r squared sine of theta d phi. So this is what I have to solve. I'm not sure if you guys have set up surface integrals before. In this class, it's never too complicated. We're only ever interested in one surface integral, and that's of a sphere. And so we're going to integrate from 0 to 2 pi. That's the integral with respect to phi. And then we're going to do our integral with respect to theta, which is 0 to pi. We were given p here, which is A0 sine theta over r squared, and then we need to multiply by the ds element, which is just r squared sine theta d phi, right? That's the differential surface element on the sphere, ds right there. So I have to perform this integral right here. And so immediately what I notice is that the r squares cancel and the sines multiply through. So I can get p rad is equal to the integral from 0 to 2 pi, integral from 0 to pi, A0 sine squared theta d phi. Okay, so how do I approach this? In a double integral, you take the first integral, calculate that, put the result of this integral into the second integral. So to do that, I need to find the result of 0 to pi, A0 sine squared theta d theta. And so the result of this integral is the A0 is a constant, it gets pulled out front. I have to look up in a table of integrals what the result of sine squared is. If you remember that, you're better mathematicians than I am. I don't, but looking in a table of integrals, I found out that that's A0 times theta divided by 2 minus sine of 2 theta over 4. And then, of course, I need to evaluate at my upper and lower bounds of my integral. So I evaluate that at pi and 0. The result of that math is A0 pi over 2. So now I need to take this and plug it into this integral. So p rad is now equal to the integral from 0 to 2 pi of A0 pi div 2 d phi. So to solve this, A0 pi over 2 can just be pulled out front. And I need to take the integral from 0 to 2 pi of d phi, which is just phi evaluated from 0 to 2 pi. And so I get a total power radiated by this antenna of A0 pi squared watts. Now I need to compare that to the total power radiated by an isotropic emitter. And so P rad for the ISO is going to be equal to the surface integral, which is again 0 to 2 pi, integral from 0 to pi. Well, now I need to think a little bit about an isotropic emitter. I was given a radiation density of A0 times some sort of function. Isotropic emitter emits that radiation equally in all directions, so the radiation density of an isotropic emitter is going to have to be A0 divided by the surface area of a sphere, which is just 4 pi r squared. And then I need to multiply by r squared sine theta d phi. So A0 over 4 pi r squared r squared sine theta d phi. So this is for the isotropic emitter there. I can see that the r squares pull out, so I get a0 over 4 pi, integral from 0 to 2 pi, integral from 0 to pi, sine theta d phi. This is a little bit easier one because the integral of sine theta, everybody remembers that it's just minus cosine. So the integral of sine theta d theta is just going to be 2, and you can solve that on your own. And so then I get 2a0 over 4 pi, integral from 0 to 2 pi of d phi. And so that's just going to give me 2a0 over 4 pi times 2 pi. So the 2 and the pi's, the 4 and the pi and the 4 and the pi cancel, and a0, which makes sense, right? If I've got an isotropic emitter, this is its power density function right here. The total power is just going to be what was in the numerator. I think that makes intuitive sense in watts. So that is power density.